your lunch, and I was really inspired by Prof. Niles, the way, the passion that you show on the topic. I think he made my life very easy now, because he told you what is the cECCI patterns, all the channeling patterns and so on. So I will just write on what he just described, which is a very complete. I feel like I'm in a undergraduate club all over again. I really enjoyed the presentation. And what different is that I want to discuss about cECCI. What's the C? C is a control. So as we know, Prof. Niles just now mentioned about the blind cECCI. So we try to tilt and rotate our samples, and hopefully we can see some dislocation. But the question is, do we know that dislocation is against which orientation? We don't know. So Prof. Niles mentioned about Prof. Stefan Jefffer. We work with him to develop these things that allow us to know exactly which orientation we are looking at, and this particular dislocation of things, stacking faults and so on, is against which crystallographic plane. Right? So I will run through this with you. 15 minutes, give me 15 minutes, I will explain it, and yeah, we can go for lunch, right? I will skip this. We discussed yesterday about 7 contrast mechanisms, and one of these is channeling contrast. But basically, Prof also already mentioned what is cECCI, so electron channeling contrast imaging. So when electron passes through because of two beam condition, all the dislocation will be highlighted, right? All the effects will be highlighted, and this is what we want to see in the crystal source. So again, I call it seeing the unseen. So you will see something that you are not supposed to see, and that is the defects, right? As industry metal players, we want to know what kind of dislocation of a linear, screw dislocation, stacking fault, grain boundary, twin grain boundaries, and so on and so forth. So again, I will skip all this. We don't want to go into detail of how the grain form, the faults and dislocation form, but fundamental of cECCI, we have discussed this Kikuchi patterns, right? When electrons are diffracted. But what is the most important is that we want to make a tilt and rotate, right? We want to know which direction essentially we are looking at, and we need to use the EBSD. Then today just line up very nicely. We talk about EBSD, we talk about all the crystallographic 101, and yeah, this is just the application, right? So let's suppose you have 3D bulk materials, right? And you want to know, you want to see the defects and all that. So before this techniques, actually people will try to cut the things with the FIB, with the focused iron beam, right? And when we cut a piece, very small piece, then we put it under the TEM, then we can look at the, the diffraction pattern and so on and so forth. But one of these took about 2 hours, right? And you have these big materials, but you only cut like a very thin layer, very small. Is your sample representative? Might not, right? And you cut the second one, you waste another 2 hours, you look again, oh, it looks different. Oh dear, I need to take the third one, and the fourth one, and the fifth one, right? So it took a lot of time. What if I tell you that we can do it directly under SEM? We don't have to cut anything, we don't have to leave out, we don't have to put into TEM, university don't have to buy another TEM. But of course we have limitations, right? SEM, the accelerating voltage will not be high as TEM. TEM 200 kilovolt, SEM is about 30 kilovolt. So there is a limitation, I will not deny that, but it will give you a faster workflow, right? So your throughput is faster. So that's what I call the paradigm shift, right? So direct defect observation in cECCI. So you saw this picture earlier. I don't want to go into detail again, but basically we use the EBSD to look at the pattern, and we want to know which orientation. Then we can choose which orientation, right? And we will feed it to our software, and we will do simulation. I will brief you in the next slide. Okay, so first of all, we need to go to EBSD. We take the EBSD raster, and we will find the orientation. So we have a lot of grain here. For example, I want to know the defect at this particular grain. I need to read the Euler angle. I go to the other grain. I will go to the other orientation. We need to jot down these 3 numbers. We call it Euler angle. Euler angle basically how they describe which orientation we are looking at against the fixed 0, 0, 0 positions, right? So we got the Euler angle. We go to the simulation software. We call it POCA software, and we will enter the Euler angle from the EBSD, right? Then we already know we want to look particularly at this particular grain, right? So we enter the information and all the simulator pattern, the stereographic, everything will come, right? And when we have this, then we are looking, right? Then the edge is where everything will in the channeling condition, the two beam condition. So we will use the simulation software just to move the crosshair to this on this line, right? And we know exactly how we should tilt and rotate our microscope. So we are not blindly tilt and rotate our microscope. No. Once we get the information, what we do, we go to the SEM, right? And we tilt and rotate as the software tells us. So it's called an educated guess, right? So we know exactly this fault against which kind of crystallographic orientation. Am I being clear here? So this is really a very great tool for you guys who work in the metal or material science research. Then from there we can look at all the we can do the analysis and stuff. Promotion. You have the best microscope here in the facility. You need one more software. You have the great EBSD from EDEX. Perfect. Perfect match in heaven. You just need one more software, then we can do all this research here. Alright? I don't want to talk about this, sorry. Okay, couple of application, then I will end the talk with a video to show you in 3 minutes how the whole workflow being done. Alright? Application, so if you have nano indentation on the tube still, right? FEMN still, and when we do these Burgers factors. Burgers factor show us the lateral distortion directions, right? And we will be able to see all these, all the effects and dislocation, right? Now you imagine we are doing, arrays, and if every sample you need to cut the TEM and do it, you will spend 20 years in your PhD, guaranteed, right? But with this technique, we do annotation, we can look directly, right? So you will spend a lot less time, and you can save some money from your professor research grant, right? So these are the techniques. Yeah, so hydrogen embrittlement, we mentioned a bit yesterday on the hydrogen embrittlement, how actually we can, before hydrogen charging and after hydrogen charging, what is the difference and so on and so forth, right? I will go through very fast, but if there's any interest, we can of course discuss it over the afternoon. Fatigue, we do a couple of fatigue tests, 50 cycle, 100 cycle, then we will see what kind of dislocation come out. All right. Fatigue, I think this is the same picture that Prof. Miles was showing just now. Yeah, so we can see the dislocation and so on and so forth. We want to calculate the dislocation density, for example, right? In this small area, what is the dislocation density? So we can take the pictures and we can use some software to do counting for us. And by the end of the day, we can say, okay, our dislocation is 5 times 10 to the power 14 per meter square, right? Because we extrapolate the size. So this is one of the things we can do. Seeing the crack formation, the grain boundaries. Hydrogen embrittlement is again the case that we are working on. So you can see the defect is against these Burgers factors, right? So we know exactly the orientation we are looking at. This will create a lot of value to your research rather than the blind disease there. Pyrite, again just another example. I will show you one on the trace analysis. So let's suppose we have this all the dislocation, right? And there's a stereographic projection. This one you can get actually from the TOCA software. The TOCA software will generate, because when you enter the Euler angle to the software, it will give you this. Okay, so you know exactly which direction you're looking at, right? Now you have the image, then you can see you can observe some dislocation, right? Like this, yes, and you can see like this, correct? So all this we can plot it. Yeah, all the dislocations, all the different okay, not this one, the next one. So yeah, this the one. So for example, you have this plane, right? All these dislocation is actually, if you draw it there, is perpendicular. You need to draw a factor that perpendicular to that. This is called a stress analysis. So we know exactly this is against which crystallographic plane, right? So we can do all this. Gallium nitride is amazing materials that warrant all this cECCI research on, also semiconductor materials. Stress analysis, yeah, this is the slide I'm talking about. So let's suppose you have a blue line, right? When you draw the blue line, right, you go back to your, you can superimpose this in a one PowerPoint slide, right? You put your picture in, you draw this line, right? And you draw perpendicular to it, correct? And perpendicular to it, you will hit at this line, right? So meaning this particular S dislocation is against -1, 1 plane. Okay, then you can do the same thing for the green line, right? Green line is like this, then we draw perpendicular, correct? Then we know, then we track, okay, probably it's 1, 1, 1 plane, and so on. So this will create value to your research, this stress analysis, right? And so on. Summary. I keep my promise to keep very short. Summary. cECCI is actually a TEM-like characterization that can be done in the SEM, right? But samples, because the argument is always when you cut into small TEM slice, I will not say it might not be representative. But when you do this in the SEM, you can choose any spots within your field of view, right? Our field of view is 12 millimeters, very big one. You can go all over the place and do this analysis. Right, we can calculate this location density. And just to tell you the difference between cECCI method and TEM method, of course, the lecturer resolution, we cannot beat TEM. As I say, the voltage is different. Depth of propagation may not be able to beat TEM as well, right? But we can see much larger area, 10 to the power 8 to 10 power 4, almost 10,000 times. And the sample is bulk, it's not a thin form, right? So when you are using this, actually there's a couple of applications. If you work on metal, super alloys, steels, aluminum, magnesium alloys, semiconductors, gallium nitride, ceramic materials. If you want to see all the the dislocation, interaction, and minerals. All right. With that, I will show you one video to show you the whole workflow, from the EBSD all the way to the 3 minutes. Then we go for lunch. I hope I can bring it here. Yes. Okay. So this is our. I mean, you saw the software yesterday, and when we tilt the sets to 70 degree, right? Now we tilt 70 degree. We want to see the EBSD, right? We do EBSD. My apologies. This is not EDAX software, but rest assured, EDAX is the best in the market in India for now for the EDX. So we acquire the map. After we acquire the map, then we can choose which grain we want to see, right? Audio. Okay. Then we choose the grain. Now we get the Euler angle. We will tilt back to 0 degree, right? We'll tilt back to 0 degree. Then we will open our TOCA software, the simulated software. You remember to enter the information. We insert the BSD detectors. Okay, this is what you look at. Looks very. I mean, this particular sample that I'm working on, so it's not a perfect sample, not fully polished. But let's suppose I want to see this soon. Okay. Okay, we want to see the defect in there. So what we do next is we go to TOCA software, set up the. Just now Prof mentioned about the different crystal structure, the graphites, and so we need to know exactly what materials. So if you're working on HCP, don't put FCC. You won't be able to see. It's a wrong. So this is a FCC sample, fresh center cubic. Then we enter the Euler angle at the side. Now the orientation comes. Then we need to move this cursor to the equity patterns, right? Yeah. So we move. Okay. Now dark. Okay. In the dark position. Then we read from the software how much we need to tilt and rotate. Okay. Once we got that, we go back to the software, and we do exactly the same. We do the tilt and rotate and the tilt with tick, and you will realize that this area becomes darker in color, meaning we are in the two beam condition. We are in the channeling conditions, right? When we are in the channeling condition, they will zoom out a bit. Yeah, then we can see all the dislocation appear. Okay, so this is a very educated guess on what we want to see. Okay, yeah, and I mean we can move it around, and you know, if we want another grain similar, go back to EBSD, copy the Euler. What I normally do is that when I'm in EBSD, I noted down couple of Euler angle, so I don't need to keep tilting, right? So I got a list of Euler angle I want to see. Then yeah, just do the simulation one time, and so ZEISS offer this solution, right? So you, as I say, you have the best EDX, you have the best microscope. Why don't you add another software to enhance your capability? And this could be a game-changing tools for you. With that, I will thanks for the time, for the graciousness of the EDX team to allow me to squeeze 30 minutes of the time to do this. Thank you very much.